interest in 3D printing myself, and Dr. Lincoln knows. Dr. Lincoln is my lab director as well as the faculty advisor of the SME. My whole story is that when I saw the video of the National Geographic, when the guy takes a wrench to some facility and they reproduce the printer wrench actually, and when the whole thing moves, when they take out the wrench and the whole thing moves, man, I just saw that video and it was amazing, seriously. I mean, I was out of my mind. So when I heard from Dr. Lincoln that Mike from Sandia National Lab has given us his think about having competition which involves 3D printing, it was great. It was great. What I want to do, I want to introduce who's right now with us. As I introduced Dr. Lincoln, our faculty advisor, and yeah, thank you, and Dean of Associate, Graduate, and Research, Dr. Jean Vandergeest. That's right. Thank you for coming. Thank you so much. And Dr. Mark Rashid is our one of the judges. He taught me the Engineering 104 solid mechanics previous quarter. So without further ado, I want to introduce you to the Sandia team. They will talk about the project. I'm sure you guys are all waiting to understand what is that piece of paper that you're seeing. And I don't know if you have any good ideas what this project is going to be. So I want to introduce Mr. Mike and Mike Harwick from Sandia National Lab. Please help me.
Yeah, thank you. This is really a great turnout. I'm really excited about this opportunity. I wanted to provide some high-level context. I know there's at least one person here who knows who Sandia is, or what Sandia is, Alex. But the rest of you probably don't. So I wanted to give you very briefly some high-level information about Sandia and about why we're interested in 3D printing. My colleagues are going to come up after me and provide a lot more detailed information about the project itself. So let me start doing that with just, yeah, thanks. Sandia National Laboratories is one of the laboratories in the Department of Energy's complex. And we're specifically run by a semi-autonomous arm of the DOE, Department of Energy, called the National Nuclear Security Administration. We have a couple of sister design laboratories who I'm sure you've heard of, Lawrence Livermore National Laboratories and Los Alamos National Laboratories. And we are all three national security laboratories, very diversified. At Sandia, we have four major program areas, those being, very quickly, defense systems and assessments, which is an area where we, it's really focused on the intelligence collection and analysis for national security, where we do a lot of work on imaging radars and satellites and such. We have a program on energy, climate, and infrastructure security, and big parts of what we do, especially here in Livermore, is combustion research. We do climate modeling, and then figuring out ways to protect critical infrastructure elements like the electrical grid, water supplies, and things like that. Another element is international homeland and nuclear security, which is really focused on detecting and protecting against chemical, biological, and nuclear threats. And then the last one, which is the one where I come from, I've spent most of my time in, is the nuclear weapons segment of it. And our job here is to maintain a safe, secure, and reliable nuclear deterrent for the national policy. And this is the element where we do a lot of our detailed engineering work. It's engineering work at a very grand scale, so very, very large projects, multi-billion-dollar projects. And it's really a motivation for this particular effort itself, at least in a kind of a generic sense. As you know, additive manufacturing is becoming very, very popular, and lots of folks are trying to figure out how they're going to use it. The aerospace industry has figured out some really neat applications so far. And we, within the complexes, we're entering an era of modernizing our deterrent. We're trying to understand how we might use additive manufacturing as well. From my perspective, one of the real advantages is it's going to help our design engineers think about their designs very differently. With conventional machining processes, we're quite limited to the way we think about our designs and the way we can actually fabricate our designs. With additive processes, there's an option space out there that frankly our engineers haven't been used to thinking about. It's really, really new. We've seen, in fact, some hybrid machines, maybe you've seen them, prototypes from Morisaki, that combine additive and subtractive processes on one platform. And these are things that really open up options for design engineers. And so what we want to do is be able to energize our engineers and energize you with new ideas and put innovative ideas into our product. Let me go on to the next one real quick. This doesn't show up really well. I wanted to give a little bio of myself, and we've got a hierarchy, project hierarchy here that is very generic in the sense that top box, it says customer and sponsor. For me, that means typically the NNSA, so our National Nuclear Security Administration, sponsors and partners in the military. That is what we provide goes to them. This box says Systems Engineering Team, and that's who I represent right now. Below that is a set of components that feed into the system that ultimately feed into the sponsor. And so what we're going to be asking you to do is think about a component level design, and that's what you see in this paper. And Dorian and Danielle are going to talk a little bit more about that. But I wanted to point out that in this particular scenario, we're in the middle of a conceptual design and feasibility phase for the project. And so from a systems engineering perspective, I'm not really sure what you as component engineers are going to be able to provide to me. But I have some goals that I'm trying to communicate to you, and you're going to help me figure out what you're able to do for me. So I've got a problem here where at a system level, I'm very, very constrained with volume and weight. And so any product that I put together has got to be small and as lightweight as possible. One of my jobs as a systems engineer is to put all of these things together, all of these components, yours and everyone else's, and package them in a way that I can meet my volume and weight requirements. Now, what Dorian will show you later is that typically these gas reservoirs, gas bottles you call them, don't pack very well. And so I think that with additive manufacturing processes, we can probably design them differently so that I can package them into a system in a way that better resembles a game of Tetris than it does in just putting a bunch of marbles in a bag and, compacting them. So that's what we're going to be asking you to do here. Again, we're in the conceptual design phase, so you're going to help us. We don't know exactly what the requirements for the system for your component are going to be yet, but we do have some draft documents, and those are the things that you see in front of you. So we're going to ask you, from a systems perspective, to give us what you can do. Show us what you can do with innovative designs for gas reservoirs. And hopefully, you can meet all the draft requirements that we're laying upon you. It may be that you can't. If you can't, then we go back and forth and we negotiate until we find a design space that works for you and works for the system. Let's go to the next one. One of the things that's inspiring about AM, and this is a GE additive manufacturing design competition photo that I like to show to people. If you're interested in additive manufacturing, you've probably seen it already. But they wanted to reduce the weight of a mounting feature that originally weighed 4.5 pounds. And that was, it's a cast and then machined part, so it's solid. But to carry the load that this particular part needed to carry, didn't need to be solid. There was a lot of extra material in the design that did need to be there. And so from an additive manufacturing process, they essentially hollowed it out and put stays inside to give it the strength that it needed to carry the loads that were required, and reduced, see, the weight significantly from 4.5 to 0.7 pounds. And so these are the things that we think we can do. Of course, this cannot be machined with a conventional process, a subtractive process. Really, this was enabled by additive manufacturing processes. And this is the sort of thing we'd like to be able to do with our parts as well. And finally, I think I'll leave this here and let Dorian talk about conventional reservoirs and something else that we're thinking about.
Thanks, Mike. So my name is Dorian Balch. I've been at Sandia for about 11 years now, and for most of that time, I've been working in what Mike referred to as one of the component areas, My background is actually not mechanical engineering, it's material science. I'm a metallurgist. And within what's called our gas transfer systems department, I've got one of the main design roles in designing and certifying new pressure vessels for use by our end customers. What's shown on the left is it's not one of our real reservoirs, but it's a typical kind of prototype. These pressure vessels are manufactured using very conventional processes that haven't really changed for 50 years. So we start with stainless steel bar. Our production facility buys thousands of feet of custom stainless steels from a couple of different steel manufacturers. These are cut to short lengths and then go through a multi-stage forging process. We use closed die forging to create a forging that would look more or less like half of a pressure vessel, but of course much larger. And then the exterior surfaces of that forging are machined down to create this shape. What's shown here is a weld. We would typically take two forgings, machine them, weld them together with very conventional welding processes. We use gas tungsten arc welding and electron beam welding, perhaps not so typical on the electron beam welding side. And that would create a closed volume that we could then fill with gas, certified for testing, and then send out to our eventual customers. That sort of very conventional forging process, or a manufacturing process, forging, starting with steel bar, forging, machining, welding, doesn't give us a lot of flexibility in terms of the designs that we can field. In the end, our pressure vessels almost all look like spheres. The ones that don't look like spheres look like cylinders. Pretty typical pressure vessel design. So, as Mike said, our eventual customer is the DoD, the military. But our immediate customer is a systems group that is trying to package our components, our pressure vessels, together with a lot of other components. And what space we are allotted doesn't always match very well with the shapes of our conventional pressure vessels. What we'd love to be able to do is take advantage of new manufacturing techniques like additive manufacturing to fill a space like this. This actually might not be that different from the sort of mechanical envelope that we're given by a systems group. This is the space. A mechanical envelope tells us this is the space you're allowed to work within. You can't go outside. This would be to fill this space efficiently with a pressure vessel made by conventional manufacturing processes, which is very difficult. Through additive manufacturing, we're hoping that you folks could generate some designs to show how an additive manufactured pressure vessel can fit in that space, maximize the usable volume, maximize the amount of gas that can be delivered, and that's really what we, even internally, are hoping eventually to get to. So I think this will be a very interesting learning process for all of us. I think everyone has the problem statement. So I think some of the problem statement Mike and I have already touched on, where our customer, a systems group, is operating under severe space and weight constraints. We are given a certain mechanical envelope. Does everyone have drawings as well? So there are a couple of drawings. The first outlines that mechanical envelope with actual dimensions. So this is the space in which you're allowed to work. And as Mike said, these are currently draft requirements because we're in sort of the conceptual phase. But it's interesting to see what can be developed that will fit inside that space. Question?
Are these dimensions in millimeters like they say?
No, it's in our pressure vessels are small, but not that small. So specifically, in terms of what process is used, we have decided to focus on the lens process, linearly engineered net shaping, for a couple of reasons. It's one that we are very familiar with at Sandia. It's also one that is available here, or nearly available here at UC Davis as a lens machine in Professor Vernia's lab, which is in the process of undergoing a little bit of refurbishment, and we hope that in the few months that will actually be up and running and potentially could be used during this project. So I think I'll turn it over to Danielle, and she'll talk a little bit about the technical requirements, and then there are also material property, assumed material properties, and these are mostly actually not even assumed, these are real material properties which will be used for this project for a typical lens stainless steel.
Okay. I'm Danielle Stevenson. I'm a mechanical engineer at Sandia National Lab. I also work in the same department that Dorian works in. And so our focus is on a component very similar to the one that you see pictured here. And so I figured now that you guys have a little bit of a background of Sandia, what we do, what our department does with the gas transfer systems, we could just kind of comb through the specifications and requirements, and if you guys have any questions, this is supposed to be informal, so please feel free to ask questions. We don't want to just talk at you guys, so if you have questions, just let us know. So I figured we can just, we can just kind of go through the requirements. So that was a good first question, making sure that the dimensions are actually, in inches and millimeters.
They're in inches then?
Yes.
Okay.
So, as Mike mentioned, there's an overall system, and this is just one of many components that are going to be packaged into the system. So, size and weight are some of our biggest constraints, and so we need to take some things into consideration. So, with our pressure vessel, weight is a serious concern, and so what we're going to do as a systems engineers team is we would like to see what type of capabilities that you guys can provide, and then we'll work through, what our weight range should be for the pressure vessel. So the vessel will actually be filled with gas. I think we're using helium, right? So the content will be 2 moles of helium. And then we're actually going to deliver the gas. And so in order to do this, we're actually going to attach an 1/8" stainless steel tube to do that. But the tube routing is going to be outside of the mechanical envelope, so you guys don't have to worry about that at this moment. So we'll provide more guidance a little bit later on, I think. Let's see.
I had a, so at this
Sure.
time we just like assume an opening, or?
I think initially, I think that's probably.
I would say at this point, don't even worry about the opening.
Okay.
The systems engineers need to figure out where all the tubes and cables are going to be going in this assembly. We're not quite worried about that yet. We're confident that the designers will be able to attach a tube where it needs to be at some point in the future. And we'd work with you to define that interface. For the purposes of this project, I'd say don't worry about the tube.
And so the material that we're going to be working with is 316L stainless steel, and as Dorian mentioned, the properties that you'll need are actually on the reverse side. So I think everything you need is back there. One of the requirements that we have for the pressure vessel to make sure that it's safe is to, for our stress, our maximum stress will need to be less than or equal to 2/3 of the material yield stress and less than or equal to 2/3 of the ultimate tensile strength, and that's all. And so if you want to take a look at your drawings, so there's 2 drawings. So there's the mechanical envelope, which is represented in this graphic, and then there's also a mounting fixture. That plate, round plate, your pressure vessel will be mounted to that. I think, is everyone?
Let me just, we haven't printed the technical drawings as much as we printed the actual problems here. So if you can share it with each other. But we have 2 of the mounting surfaces. Anyone? You guys have? All right, there you go. Take it.
let's see, maybe Farhad, you could talk about the deliverables for this project, the prototypes that we're going to be building.
Sure. So as far as I understood, we're gonna the teams are gonna produce two types of prototypes. One is the actual vessel, and the other one is the one that you're gonna show a section view. So it doesn't matter how you're gonna put the section, but it's gonna be up to you, up to the teams, to how to show the section view. And
Yeah, that's good.
That's it.
And really, I think what you want to do is select the sections that is most instructive to the systems folks, so we understand how you're achieving this, the ability to hold the gas. And those will be in plastic, of course. But the intent at the end is to hopefully with called the winning design, and maybe talk about how you're going to do those too, but actually produce this out of metal. And as was mentioned, we're trying to get the lens machine that's in Dr. Lavernia's laboratory up and running. I hope that we're able to do that within the time frame of this contest and then have enough extra time to build one of the parts. If not, we're also looking at perhaps other opportunities, other places where we might be able to get this done. So we'll be working that as you're working the process here.
So before you start talking about the judging criteria
Right.
on that, so I just forgot to mention one thing. So what we are really concerned about and what we're very interested in seeing is with your designs, we'd like to know how much gas can your pressure vessels actually hold if it can't, completely hold the entire amount of the 2 moles of helium. What your volumes are, the weight of your pressure vessels, and the maximum gas pressure inside. So those are some of the design characteristics that we will be most interested in.
Good. Okay, great. Thank you so much. Well, what I think is the best is to give a break. That if anyone wants to grab something, they can grab something, and after that we start any other questions that you guys may have, and we're going to talk about what we have scheduled for this whole competition. It's not like we have a kick-off and it just goes and we come back all in the end of this quarter. So it's not like that. We have we have scheduled some events to happen in the middle of the whole competition. So what I suggest is to have a break. Yes.
Maybe before you break,
Yeah.
I wonder if it wouldn't be useful to give a little guidance or maybe expand on the item 3 under the deliverables, which calls for plastic models, and in particular the digital format, for example, that a CAD file would need to be in, or the interface,
sure.
and where's the machinery, how can teams access the machinery to make those models and this kind of.
The good news is we have a whole. I'm gonna talk about them. So good news is I have reserved a tour for a team center. Anyone knows about the team center at the BGSF, the biomedical center that we have? Anyone from you guys?
Yeah.
Well, great. So it's a brand new facility. I walked in it and I was amazed with the printers that they have. So it's at the BGSF and it's on the side of biomedical side. And in EFO we do have a printer, but when I wanted to print something in previous quarter, I ran into trouble. So I'm not sure yet if they have fixed the problem and if that's going or not. But for next week, Friday, we'll send out email to everyone. We have a tour of that facility, the team facility in our biomedical center. So you want to continue?
Just to interject something, in general, the team is going to be up to the teams themselves as to where they want to print at. These are certain resources, obviously the team center, BGSF, the lab, the EFL, but we also recognize that since you're here interested in the 3D printing, some of you may have a printer. Some of you may know somewhere else that has a printer. There are other locations off campus that do have printers as well. And so the materials and the costs of the printing is going to be part of the team fund that you're going to have to use for resources. And so it will actually be up to you whether or not you want to use, say, the selective laser sintering, or however, I know that's not necessarily classic, but whatever method and whichever machines that you would like to use in order to complete these models.
Right. We can talk about the process of 3D printing. I mean, I don't have that much of an experience in it as of now, but for sure we can talk about how Dr. Rashid asked about how you're gonna do the modeling and then you're gonna extract it as a STL file and send it to the printer, the 3D printer. So yeah, definitely. So what I suggest is a break, and after that I can show you the schedule, and if you have questions, I hope you can ask the Sandia team, and yeah. So if you want something, grab some, and if you haven't signed in, please sign in for us. Yeah, come back.